The future of our galaxy is a subject that captures the imagination of many, not only because it involves the grand-scale cosmic dance of two enormous systems, but also because it touches on how our entire cosmic environment might look billions of years from now. While the idea of a galactic collision sounds dramatic, almost apocalyptic, it's important to understand the dynamics that govern these events and why, despite their spectacle, they are generally not catastrophic for individual stars or planetary systems like our own solar system. To grasp what will happen when the Milky Way and Andromeda collide, we first need to understand the scale and structure of these galaxies. Galaxies are massive collections of stars, gas, dust, dark matter, and other celestial objects, bound together by gravity. The Milky Way, our home galaxy, is a barred spiral galaxy containing roughly 200 billion stars, sprawling over a sprawling disk about 100,000 light-years in diameter. The Andromeda Galaxy, known as M31, is similar in size and shape and contains around 1 trillion stars, making it even larger in terms of the number of stars. Despite their enormous sizes, the stars within these galaxies are separated by immense distances, light-years apart, meaning that, on average, there is plenty of space between stars even as these galaxies eventually collide. The process of galaxy collision is not a sudden event, but a prolonged series of interactions that unfold over billions of years. Current estimates suggest that the Milky Way and Andromeda will begin to interact gravitationally in approximately 4.5 billion years, with their cores expected to merge around 6 billion years from now. But there is no need for immediate concern, because space is vast, and the individual stars within these galaxies are tiny compared to the distances separating them. When galaxies collide, what happens is more a matter of their gas clouds, dust lanes, and dark matter halos interacting, influencing star formation and the overall structure of the galaxies, rather than stars smashing into each other en masse. To understand why stars are rarely hit during these grand galactic encounters, consider the scale again. Even though galaxies are enormous, their stars are relatively tiny points of mass separated by millions or billions of miles. Imagine an air traffic controller managing traffic in a city with millions of airplanes, each plane flying at great distances from one another. Even if many planes are in the sky at once, the chances of two planes colliding are minuscule because they occupy distinct spaces, follow different paths, and are separated by vast distances. Similarly, in galaxies, despite the gravitational chaos of a collision, the probability that two stars will directly collide is incredibly low. What does happen during these interactions is a reshuffling of gas and dust clouds inside the galaxies. These clouds are the raw materials for new stars. When galaxies collide, their gas clouds can collide and compress, igniting intense bursts of star formation, sometimes called starbursts, creating new generations of stars and planetary systems. This process can produce spectacular regions of glowing nebulae and clusters, enriching the galaxies with new stars and shaping their structures in dramatic ways. The gravitational pull during a collision causes the galaxies to stretch and distort. Instead of a quick smash and merge, the galaxies go through a series of close encounters, during which their shapes can be heavily warped. Over time, these interactions lead to the formation of new, larger galaxies, often elliptical in shape, through a process called galactic cannibalism, where one galaxy absorbs another. The final outcome of this cosmic encounter will likely be a single, larger elliptical galaxy, sometimes called Milkomeda, a name some astronomers have playfully coined for the merged galaxy. This process is not unique to our galaxy and Andromeda. Galaxy collisions have been observed across the universe for billions of years. Colliding systems like the Antennae galaxies and the Mice galaxies showcase spectacular examples of galactic interactions, with tidal tails and starburst regions vividly visible. These images help astronomers understand how galaxies grow and evolve over cosmic time, illustrating that collisions are a fundamental aspect of galaxy evolution, not rare and destructive events. Even so, the long timescale of these events reassures us that the collision will not be an immediate threat to our solar system. Our Sun is currently about 26,000 light-years away from the galactic center, well outside the dense core regions where stars are packed more tightly. During the eventual collision, the Sun's position in the galaxy is unlikely to change dramatically, and the chances of our solar system being directly disturbed by a stellar encounter are exceedingly low. In fact, many stars will drift apart and become part of new stellar neighborhoods after the merger, while planetary systems like ours will largely remain intact throughout the process. However, this cosmic upheaval will have profound effects on the galaxy's appearance and the environment of its stars. The fresh gas clouds compressed into new stars will change the galaxy's brightness and shape, offering a dazzling display of star birth. The central regions might become more active with black hole activity or star formation, and the galaxy's spiral arms will likely become less defined, transforming into a more featureless elliptical structure. For astronomers observing the universe from afar, it will be a spectacular natural experiment in galaxy evolution, playing out over billions of years. Understanding this process also sheds light on how our own galaxy has been shaped over cosmic time. In fact, the Milky Way has likely undergone multiple mergers in its history, including interactions with smaller dwarf galaxies and satellite systems. These minor mergers have contributed to the growth of our galaxy's halo, its stellar populations, and its overall structure. The upcoming collision with Andromeda is just the next chapter in this ongoing story of cosmic development. It's important to recognize that these events are driven by gravity, an ever-present and unyielding force that keeps galaxies bound together. While the collision itself can produce dramatic visual effects, gravity ensures that, on the scale of stars, the universe is remarkably resilient. Our planet and solar system, already comfortably orbiting the Sun, are unlikely to face any catastrophe directly caused by the large-scale galactic collision. Instead, the outcome will be a new, larger galaxy that will continue to evolve over the next many billions of years. The concept of the universe's stability amid such colossal changes is both humbling and fascinating. It highlights how cosmic processes unfold over timescales vastly different from human life, reminding us that the universe is a dynamic place, constantly changing on a grand scale. These galaxy interactions serve as a natural laboratory for scientists to understand the forces at play in shaping the cosmos, revealing that even the most titanic events are governed by the same fundamental physics that we observe in everyday life: gravity, motion, and the interactions of matter and energy. The eventual merger of the Milky Way and Andromeda will be a testament to the slow but relentless evolution of the universe. For now, the best we can do is observe and understand these phenomena from afar, appreciating the natural beauty of galaxy interactions and the knowledge they yield about the universe's history and future. It's a reminder that, although our own galaxy's future may involve a spectacular cosmic transformation, the universe as a whole is characterized by processes that are both vast and peaceful, unfolding over billions of years with a silent, steady grace. As we delve deeper into what will happen when the Milky Way meets Andromeda, it's essential to understand the scale and mechanics of such an event. Galaxies are immense collections of stars, gas, dust, dark matter, and other cosmic components held together by gravity. Each galaxy is like a sprawling universe in miniature, with regions that are densely packed with stars and others that are more diffuse. When two galaxies begin to interact, it's primarily their vast clouds of gas and dark matter that encounter each other first, leading to dramatic effects that shape the future of both systems. The process begins long before the two galaxies actually merge. As they approach, their mutual gravity causes distortions in their respective structures. They start to tug on each other, which can lead to the formation of tidal tails, long, stretched out streams of stars and gas that are pulled out from the galaxy's disks. These features are like cosmic fingerprints, evidence of a past gravitational dance that stretches and stretches the galaxy's arms. Astronomers can observe these tidal tails in nearby galaxy collisions, such as the famous antennae galaxies, which display spectacular arcs of stars and gas flung out into space. During this pre-merger phase, the gravitational forces also cause disruptions within the galaxies themselves. The dense gas clouds, mainly composed of hydrogen and other elements, become compressed as the galaxies collide and their structures intertwine. This compression acts as a catalyst for starburst events, where stars form at an extraordinarily rapid pace, sometimes creating thousands of new stars within just a few million years. Whether in the early stages of interaction or during the actual merger, these bursts of star formation can temporarily increase the galaxy's brightness, giving it a luminous glow that astronomers can detect millions of light years away. It's important to emphasize that, despite the grandeur of these events, individual stars rarely collide. Space is so vast, and the stars are so tiny compared to the distances between them that the odds of two stars actually hitting each other remain exceedingly low, even during galactic collisions. Instead, what happens is that the gravitational forces rearrange the orbits of stars and gas clouds, causing some stars to be flung into new orbits or even ejected into intergalactic space. The overall structure of the galaxies is what's dramatically affected, with their shapes transforming over billions of years. Dark matter plays an especially crucial role in the process. It makes up about 85% of the total mass of a galaxy, yet it's invisible and interacts only through gravity. When galaxies collide, their dark matter halos, vast, invisible spheres surrounding the visible parts, overlap and interpenetrate. Observations and simulations suggest that these halos pass through each other relatively unscathed, because dark matter does not readily interact with itself or normal matter, apart from gravity. This passage helps in dissipating energy and distributing matter during the merger, ultimately aiding in the coalescence into a new galaxy. Throughout this entire process, gravitational interactions act as the cosmic glue, binding and shaping the evolving structure. The long timescale involved means that the collision unfolds over billions of years. To put this in perspective, the current separation between the Milky Way and Andromeda is about 2.5 million light years, and they are approaching each other at roughly 110 kilometers per second, about 68 miles per second. Despite this relatively swift speed on cosmic scales, the journey to a complete merger will take another 4 to 6 billion years. Interestingly, the initial approach sees the galaxies maintaining much of their original features. Their spiral arms, for example, are still recognizable at first, although gradually distorted. As gravitational tug-of-wars continue and the galaxies become more intertwined, their shapes will become more irregular. The galaxy merger model predicts that the two disks will eventually blend into a more spheroid or ellipsoidal shape, a process that turns the familiar spiral galaxies into something more like elliptical galaxies, which tend to have a more rounded, featureless appearance. Simulations have provided valuable insights into this transformation. They show a sequence of overlapping, complex interactions where multiple close passages occur before the galaxies fully coalesce into a single entity. During these passages, the galaxies can exchange gas, stars, and dark matter, leading to the mixing of stellar populations from both galaxies. Over time, the original structures fade away, leaving behind a galaxy that is larger, more massive, and with a different shape than either of the initial galaxies. One of the most intriguing aspects of this cosmic collision is the fate of the galaxy cores. Both the Milky Way and Andromeda have supermassive black holes at their centers. The Milky Way's black hole, Sagittarius A, and Andromeda's black hole, known as M32. As the galaxies draw closer, these black holes, each millions of times more massive than our Sun, also come into mutual influence. Over billions of years, it's expected that these black holes will eventually gravitationally pair up and form a supermassive black hole binary. This binary will continue to spiral inward, emitting gravitational waves, a phenomenon predicted by Einstein's theory of general relativity that will eventually cause them to merge into an even more massive black hole. The merging of these giant black holes is among the most energetic events in the universe, releasing enormous amounts of energy in the form of gravitational waves and electromagnetic radiation. These waves ripple through spacetime itself, traveling across the cosmos. Although detecting these waves on Earth remains very challenging, future observatories like the Laser Interferometer Space Antenna, LISA, aim to capture them. Understanding black hole mergers is not just about galaxy evolution. It also provides insights into fundamental physics and the nature of gravity itself. Moving beyond the structural and gravitational effects, the inner regions of the future merged galaxy are expected to experience unusual activity. As gas clouds pour towards the galactic center, the feeding of the central black hole could intensify, igniting what astronomers call active galactic nuclei, AGN. During such active phases, the black hole can emit vast amounts of energy, sometimes outshining the combined light from billions of stars. These energetic phenomena influence the galaxy's evolution, driving powerful outflows of gas that can suppress or trigger star formation in different regions. While much of this cosmic drama unfolds over billions of years, it also injects a sense of perspective into our understanding of time and change. The collision itself is a slow dance, yet it produces profound transformations, reshaping the galaxy's fundamental character. From a human perspective, this event is billions of years away, a timeline that stretches beyond human history and into the distant future of the universe. For that reason, our current observations are vital. They preserve a snapshot of galaxies in different stages of interaction, helping us piece together the story of cosmic evolution. In essence, the impending collision between the Milky Way and Andromeda is not just a wild celestial event. It's a natural outcome of the universal laws governing gravity and motion. It demonstrates how large-scale cosmic structures grow, evolve, and sometimes collide, contributing to the grand narrative of the universe. These events are reminders that galaxies are dynamic, ever-changing systems, subjects of the universe's slow but relentless process of transformation. Although it will alter the appearance and structure of our galaxy, the collision is unlikely to threaten the planets and life within our solar system. Instead, it offers us a direct view into the cosmic processes that have shaped our galaxy's history and will shape its future, giving scientists an extraordinary natural laboratory to explore the fundamental forces that govern everything from tiny particles to sprawling galaxies. As the two galaxies continue their gravitational dance, one of the most fascinating aspects of their impending collision involves the fate of individual stars, planets, and other celestial objects within those galaxies. Despite the dramatic scale of these encounters, it's important to understand that most stars are separated by vast distances, so direct collisions between stars are exceedingly rare. Instead, what occurs is a reshuffling of their positions, with stars being scattered into new orbits or even ejected entirely from the merged galaxy. This process, over millions to billions of years, leads to a redistribution of stellar populations and the creation of a more homogeneous, spheroidal galaxy. The positions and movements of stars in the Milky Way are typically stable over long periods because the distances between them are enormous relative to their sizes. For comparison, our Sun is about 93 million miles from the next star, Proxima Centauri. During galaxy mergers, the gravitational forces can perturb stellar orbits, causing some stars to be thrown into the outskirts or flung out into intergalactic space. These ejected stars, known as hypervelocity stars, can travel at tremendous speeds, leaving their home galaxy entirely. Such stars serve as cosmic messengers, providing clues about the violent gravitational interactions that occur during galaxy collisions. While the chances of our sun being directly impacted during the merger are virtually nil, since stars are spread so far apart. The sun's position relative to the galaxy's core and the overall gravitational environment could change. Some models suggest that the sun's orbit might shift, and in a very long timescale, it could find itself in a different part of the resulting galaxy. Interestingly, this means that even if our galaxy's structure changes dramatically, it's unlikely that individual stars or planetary systems would be destroyed outright. The scale of the distances involved offers a certain cosmic resilience. Stellar systems tend to be intact even amid the chaos. Another noteworthy point relates to the fate of the gas and dust clouds within the galaxies. These clouds are the raw material for star formation, and their interactions during a merger can lead to bursts of intense star creation, known as starbursts. When gas clouds from the two galaxies collide, the resulting shock waves compress the gas, triggering rapid and massive star formation episodes. These starbursts can dramatically alter the luminosity and appearance of the merging galaxy, making it brighter and more active than either galaxy was before. Over time, however, this frenetic period of star formation diminishes as the gas supply is exhausted or expelled by energetic feedback from young stars and active black holes. The formation of new stars during a galaxy merger has implications beyond the immediate galaxy structure. Newly formed massive stars tend to be short-lived, ending their lives in supernova explosions that seed the surrounding environment with heavier elements. These elements are essential for forming planets and the building blocks of life. Therefore, galaxy collisions are not just destructive events. They also play a vital role in enriching the cosmic material from which future generations of stars and planets will emerge. In contemplating the long-term evolution of the merged galaxy, scientists also consider the formation of new stellar populations with different chemical compositions. Because each merging galaxy may have a unique history of star formation and chemical enrichment, their combination leads to a diverse mix of stars with varying ages and compositions. This blend helps astronomers understand the history of galaxy formation by studying stars in different stages of evolution and with different chemical signatures. Such detailed analyses reveal that galaxy mergers are fundamental processes shaping the diversity we observe in the universe today. One additional consequence of the merging process involves the redistribution of dark matter, the elusive and mysterious substance that makes up most of the universe's mass. Dark matter does not emit, absorb, or reflect light, making it invisible, but its gravitational influence is vital for the formation and stability of galaxies. Simulations indicate that as galaxies collide and merge, their dark matter halos, the extended, invisible regions surrounding galaxies, interact and gradually settle into a new, combined halo. This new dark matter structure influences the dynamics of stars within the merged galaxy, helping shape its overall gravitational potential and stability. Understanding how dark matter behaves during galaxy mergers offers key insights into fundamental physics. Since dark matter contains no known electromagnetic interactions, it does not collide or interact in the same way as normal matter. Instead, it manifests through its gravitational effects. Studying galaxy collisions provides a natural laboratory for testing theories about dark matter's properties, such as whether it clumps into halos in predictable ways or exhibits more exotic behavior. This knowledge, in turn, shapes our broader understanding of the universe's composition and evolution. As these intricate processes unfold over cosmic timescales, the eventual result is a galaxy that looks quite different from its progenitors. A large, often more spherical galaxy with a more uniform distribution of stars, gas, and dark matter. The initial spiral arms, which give the Milky Way its iconic structure, will likely be smoothed out or replaced by a more rounded, featureless shape. This transformation from a structured spiral to an elliptical or lenticular galaxy exemplifies how the universe's grand-scale interactions drive the evolution of cosmic structures. Interestingly, the new merged galaxy will often be more massive and luminous than either of the progenitors. This is because merging galaxies bring together the stars, gas, and dark matter from both, effectively creating a larger and more energetic system. Its increased mass influences its gravitational pull, shaping the orbits of remaining stars and affecting the environment around it. The galaxy's size, mass, and shape are key data points that astronomers analyze to understand the history of galaxy interactions across the universe and to test theoretical models with real observations. Throughout this process, cosmic interactions also produce transient but powerful phenomena, such as the formation of energetic jets emanating from the central black holes during active phases. These jets are streams of highly energetic particles that can extend thousands of light years from the galaxy's core, impacting the surrounding interstellar medium. Such activity can regulate star formation by either compressing gas clouds, triggering new stars, or dispersing gas, inhibiting the birth of new stars. These feedback mechanisms are crucial in controlling the evolution of galaxies, preventing unchecked star formation and helping maintain the observed diversity in galactic structures. Fundamental to the science of galaxy mergers is the understanding that time scales involved are immense. While to human observers, celestial events unfold over moments or years, cosmic processes take millions to billions of years. This disparity in scale offers a sense of perspective and highlights the importance of astronomical observations and simulations. By observing galaxies at various stages of interaction, scientists can piece together the evolutionary sequence, providing experimental evidence that aligns with theoretical models. These studies affirm that galaxy mergers are a common and natural part of cosmic history, shaping the universe in ways both dramatic and subtle. In the grand scheme, the eventual collision of the Milky Way with Andromeda exemplifies the dynamic and ever-changing universe. It underscores the view that galaxies are not static islands of stars, but rather evolving systems driven by gravity and physics. The process exemplifies the cosmic cycle of destruction and creation, where collisions destroy some structures, but also give rise to new ones, fueling ongoing evolution. Such events remind us that, on a cosmic scale, change is the only constant. Finally, this future event serves as a testament to the incredible power of scientific inquiry. While the collision lies billions of years ahead and is beyond direct observation for now, scientists continue to develop and refine models to predict what will happen. These models are tested against real observations, from the structure of distant, merging galaxies to the behavior of dark matter. Advances in telescopes, computer simulations, and gravitational wave detectors bring us closer to understanding the fundamental processes governing the universe. In the end, studying galaxy collisions like the impending Milky Way-Andromeda encounter enriches our appreciation for the complexity, grandeur, and unity of cosmic evolution, offering a glimpse into the ongoing story of the universe itself. As astronomers prepare for the eventual merger between the Milky Way and Andromeda, they rely heavily on computer simulations to predict how such an enormous event will unfold. These simulations are a crucial tool because they allow scientists to model the complex gravitational interactions over billions of years, something impossible to observe directly in real time. By inputting data about each galaxy's size, mass, star distribution, and dark matter content, these models generate detailed visualizations of the orbital dance that will eventually lead to collision. They show that, although the two galaxies are currently separated by about 2.5 million light-years, their gravitational pull is slowly drawing them together. Over the course of billions of years, their paths will inevitably intersect, culminating in a dramatic cosmic encounter. In these simulations, one consistent theme is the importance of the galaxy's trajectories, specifically the angles and velocities at which they approach each other. Depending on these parameters, the merger can take different forms. For example, if the galaxies collide almost head-on, the event will be more violent, leading to intense starburst episodes, rapid and widespread formation of new stars fueled by the collision-induced compression of gas clouds. Conversely, if the approach is more glancing or gliding past, the galaxies may experience multiple close passes over an extended period, gradually losing their individual identities and eventually settling into a new, merged entity. These scenarios help scientists understand the range of possible outcomes and refine their expectations based on observed galaxy interactions elsewhere in the universe. One particularly fascinating aspect revealed by simulations is how the vast amounts of gas within each galaxy interact during the collision. Gas acts as the raw material for star formation, and when galaxies merge, their gas clouds collide and compress, setting off waves of new star birth. This process, called a starburst, can be incredibly energetic, producing millions of new stars in just a few million years. Such starbursts are observed in other galaxies undergoing interactions, serving as cosmic laboratories for understanding star formation under extreme conditions. The dense, chaotic environment created during the collision also stirs the galactic centers, funneling gas toward the supermassive black holes lurking there. This can ignite active galactic nuclei, supermassive black holes feeding on infalling matter, resulting in bright, energetic phenomena like quasars. While our Milky Way doesn't currently host a quasar, during the merger, the central black holes may undergo periods of intense activity, dramatically affecting the galaxy's evolution. A key process that simulations help elucidate is how dark matter influences the merger. Dark matter halos envelop galaxies like the Milky Way and Andromeda, acting as gravitational scaffolding that holds everything together. During the collision, these halos interact gravitationally, passing through each other with only minimal direct contact, since dark matter does not collide like normal matter. The behavior of dark matter plays an important role in shaping the structure of the final galaxy, helping to re-establish equilibrium after the turbulence of the merger. Different dark matter models predict varying behaviors for these halos, whether they remain intact or are disrupted. So astronomers compare simulation outcomes with observational data to test these hypotheses. Essentially, the way dark matter influences the merging process not only helps determine the shape and size of the new galaxy, but also provides insight into the fundamental nature of dark matter itself. As the two galaxies finally coalesce, the resultant structure is unlikely to resemble the familiar spiral form of either progenitor. Instead, the merger will produce a larger, more spheroidal galaxy, often an elliptical or lenticular galaxy, characterized by a more uniform distribution of stars and less prominent spiral arms. These types of galaxies are common in the universe and are often the result of multiple mergers over cosmic history. The transition from a well-defined spiral to a more rounded shape results from the violent gravitational interactions that scramble the original orbits of stars, dispersing them into random directions. For the Milky Way, this means its distinctive spiral arms will gradually fade, giving way to a more featureless, rounded appearance. Over long timescales, the galaxy becomes more stable, with stars settling into new orbits within the gravitational potential of the combined mass. While the visual transformation of the galaxy is fascinating, the process also has significant consequences for the star populations within it. The influx of gas and the subsequent starburst phase will result in the formation of many new stars, which will eventually evolve into various types of stellar remnants: white dwarfs, neutron stars, and black holes. Over billions of years, the original, older stars from both galaxies will remain, but the overall stellar population will be altered by the influx of younger stars formed during the merger. This rejuvenation influences the galaxy's brightness and color. New stars tend to be blue and luminous, giving the galaxy a somewhat brighter and more vibrant appearance in its early post-merger years. However, as the gas supplies diminish and star formation slows, the galaxy's color will shift back to redder hues, dominated by aging stars. Another intriguing aspect that simulations help clarify is how the potential for future planetary systems evolves during the merger. Despite the chaos on a galactic scale, individual star systems are usually far enough apart to avoid direct collisions even during the tumultuous merger process. However, the gravitational perturbations can alter the orbits of stars, sometimes significantly, potentially destabilizing planetary systems or prompting comets and asteroids to change their paths. These disturbances could lead to increased cometary impacts or even the ejection of planets from their stars, subtly affecting the habitability of planets during this turbulent period. In the broader perspective, the galaxy's restructuring ultimately influences the environment in which stars and planetary systems exist, though such changes occur over timescales far longer than a human lifetime. One of the more dramatic effects of galaxy mergers is the possible ignition or reignition of the central supermassive black hole. As gas and dust are funneled toward the galaxy's core, the black hole can become a fedular or active nucleus, emitting intense radiation across the electromagnetic spectrum, from X-rays to radio waves. This energetic activity can be temporarily observable as an active galactic nucleus or quasar, shining millions of times brighter than the entire galaxy itself. So far, astronomers have observed many galaxies in various stages of merging that showcase these powerful phenomena, giving valuable clues about how black holes grow and evolve alongside their host galaxies. In the future, the eventual merger of the Milky Way's central black hole with that of Andromeda is expected to lead to a more massive black hole, which could influence the galaxy's future evolution and the surrounding environment. On a cosmic timescale, the entire merger process is an extended affair, stretching over billions of years. This slow but inevitable dance is driven by gravity, with each epoch marked by subtle shifts in motion until the final collision. Understanding each phase through simulations and observations allows scientists to piece together the story of how galaxies grow, evolve, and influence their surroundings. These insights also help contextualize our own galaxy's history, tracing back through the Milky Way's past encounters with smaller galaxies and predicting its future interactions within the local group of galaxies. The grand timescale of these events emphasizes our place in a universe that is constantly changing, driven by forces we are gradually unraveling through scientific inquiry. Despite the extraordinary scale and complexity, the collision between the Milky Way and Andromeda is not an abrupt event, but rather a drawn-out process of cosmic transformation. For human observers on Earth, assuming we are still around in billions of years, staring into the night sky, the collision will be invisible for most of its duration. The night sky will gradually change, but the full spectacle of the galactic chaos will only be apparent in detailed astronomical data, taken from distant observations of other galactic mergers in the universe. Thanks to the cumulative work of astronomers, we have an increasingly comprehensive view of such events, which help us understand not just how galaxies collide, but also how the universe as a whole has evolved over epochs. Ultimately, studying the anticipated Milky Way-Andromeda merger offers more than just a glimpse into a distant future. It provides a window into the fundamental processes that shape our universe. It illustrates how gravity, dark matter, and gas interact over incomprehensibly long periods, orchestrating the grand architecture of the cosmos. By comprehending these processes, scientists gain insight into the past, present, and future of countless galaxies, including our own. As our technology advances, through better telescopes, more sophisticated simulations, and innovative methods of detecting gravitational waves, the puzzle pieces that describe galaxy interactions become clearer. These discoveries not only satisfy our curiosity about the universe's mechanics, but also deepen our appreciation of the interconnectedness and ever-evolving nature of all cosmic structures. So, while the Milky Way's collision with Andromeda is an event that will unfold long after our time, it embodies fundamental principles that govern the universe's evolution. It is a testament to the power of science to predict and understand phenomena that span billions of years and trillions of miles. By studying these colossal events, we get closer to grasping the full story of how the universe has come to be what we observe today, and what it might become in the eons to come. As the galaxies continue their slow, gravitationally choreographed dance, one of the most intriguing transformations occurs in their central regions, where supermassive black holes reside. These cosmic giants, often millions or billions of times more massive than our Sun, sit at the heart of most sizable galaxies, including both the Milky Way and Andromeda. During the eventual interaction and merger, gas and dust funnel toward these black holes, feeding them with material that can dramatically increase their activity. This process, known as accretion, can cause the black holes to become active, transforming them into ultra-bright sources of radiation called active galactic nuclei, or ANs. An active galactic nucleus is a highly energetic phenomenon, capable of emitting radiation across the entire electromagnetic spectrum, from high-energy X-rays to long-wavelength radio waves. During this phase, the black hole's accretion disk, composed of infalling gas and debris, swirls at velocities approaching the speed of light, heating up and glowing brightly. For astronomers, these luminous centers are like cosmic beacons, revealing that a black hole is actively consuming matter. When two galaxies merge, the dynamics of this process are amplified, often igniting or intensifying AGN activity. This phenomenon is not merely an interesting side effect. It can have profound consequences on the host galaxy as well. The intense radiation and energetic jets emitted by active black holes can influence the galaxy's evolution in several ways. These jets, which are narrow streams of particles propelled at relativistic speeds, can extend thousands of light years into space. They can heat or expel gas within the galaxy, suppressing star formation by depriving the galaxy's core regions of the cold gas needed to birth new stars. This process, called feedback, acts as a regulatory mechanism, preventing the galaxy from forming stars at an uncontrollable rate. In the context of the Milky Way and Andromeda, current observations suggest that their central black holes are relatively inactive compared to the dramatic activity observed in other merging systems. However, during the long merger process over the next billions of years, it is plausible that the interactions in their cores will trigger periods of heightened activity. As the black holes of the two galaxies gradually spiral inward, they do not immediately collide and merge into a single, larger black hole. Instead, these behemoths will form a binary black hole system, orbiting each other in a final gravitational waltz. Over time, gravitational wave emission, ripples in spacetime predicted by Einstein's theory of general relativity, will carry away energy and angular momentum, causing the black holes to gradually draw closer. The eventual coalescence of the two supermassive black holes is expected to be a spectacular event for astrophysicists, generating a powerful burst of gravitational waves that would ripple through the fabric of space itself. Detecting these waves is incredibly challenging due to their faintness, but future space-based observatories, such as the planned Laser Interferometer Space Antenna, LISA, aim to capture these minute disturbances. By studying gravitational waves from supermassive black hole mergers, scientists hope to learn much about the fundamental physics governing gravity and spacetime. Additionally, the merger of the black holes will likely send a gravitational wave, kick, which could displace the combined black hole from the galaxy's center temporarily or even eject it entirely in extreme cases. Such a displacement could influence the galaxy's structure and further impact star formation and the distribution of gas in the core regions. Beyond the black holes themselves, the collision event has far-reaching implications for the entire galaxy. The gravitational tussle at the center can induce instabilities that ripple outward, stirring up the stellar and gaseous content of the galaxy's inner regions. These disturbances can lead to the formation of shells, rings, or other complex structures in the galactic core, serving as cosmic fingerprints of the merger process. Over billions of years, these features gradually settle into a new equilibrium, producing a galaxy that differs substantially from its original form. The entire process, galactic collisions, black hole mergers, and the subsequent feedback effects, is a prime example of how the universe continually evolves on cosmic timescales. It demonstrates that galaxies are not static islands of stars, but dynamic entities shaped by gravitational interactions, gas flows, and the powerful influence of black holes. Each phase of this evolution offers scientists invaluable insights into the fundamental forces at play, helping to piece together the grand story of cosmic history. As researchers refine their models and observations, one important aspect they consider is how these colossal events impact the galaxy's overall structure. For example, many elliptical galaxies observed today are thought to be the remnants of past major mergers. These galaxies tend to have a more spheroidal shape and less of the spiral structure seen in the Milky Way or Andromeda. This morphological transformation occurs because the regular, orderly motion of stars in disk galaxies is disrupted during collisions. Instead, stars often end up moving in more randomized orbits, creating the oval or spherical shape characteristic of elliptical galaxies. In the case of the Milky Way and Andromeda, the eventual merger will likely transform them into a larger, more massive elliptical galaxy. This process involves not just the combination of stars and gas, but also the redistribution of angular momentum, which influences the final shape and kinematic properties of the resulting galaxy. As the two galaxies coalesce, their characteristic features, spiral arms, bars, and other structures, will gradually fade, replaced by a more centralized and smooth stellar distribution. The new galaxy will retain some memory of its past, with stellar streams or shells that serve as remnants of the merger process. But these features will gradually blend into a more uniform structure over time. The influence of black hole activity during this transformation can also influence the galaxy's central brightness and core properties. A merger-induced black hole increase in activity can clear out gas from the central regions, leading to a phenomenon called core scouring. This process can produce a noticeable decrease in stellar density near the galaxy's center, giving rise to a faint, depleted core, another signature observable in massive elliptical galaxies today. Importantly, while the grander collision and merger events unfold over billions of years, their effects shape the long-term evolution of galaxies across cosmic history. They serve as fundamental mechanisms through which galaxies grow, change shape, and develop the complex structures astronomers observe. Such transformations are not unique to our local group, but are common throughout the universe, showcasing the universality of the gravitational forces that govern cosmic evolution. As the process advances, the interactions are also shaping the environment that surrounds the galaxy. Gas streams and tidal tails, elongated features composed of stars and gas, are often flung out during mergers, extending tens or hundreds of thousands of light years into space. These structures, observable in distant merging galaxies, serve as cosmic tracers of the violent interactions taking place. Over extended periods, they can fall back into the newly forming galaxy or be dispersed into intergalactic space. Interestingly, the material ejected during these interactions can serve as fertile ground for future star formation. As gravitational forces pull gas and stars into new configurations, some gas clouds may cool and condense, leading to the formation of new stars in the outskirts or even in faint tidal dwarf galaxies, small, star-forming structures that originate from the debris of the merger itself. Thus, the merger does not solely consume or destroy, but also fosters new stellar creation, contributing to the ongoing cycle of galactic evolution. The interplay of these various processes, supermassive black hole activity, redistribution of stars and gas, and the formation of new structures, in the aftermath of a merger, exemplifies the complex yet orchestrated nature of galaxy evolution. Each event leaves behind subtle clues that astronomers can interpret to reconstruct the sequence of cosmic interactions that shaped the galaxy's current form. By studying galaxies in different stages of merging across the universe, scientists piece together the broader narrative of how galaxies assemble and transform over billions of years. In the case of the Milky Way and Andromeda, understanding these processes highlights that our own galaxy is not a static or isolated entity, but part of a larger, interconnected cosmic web. The eventual merger, while billions of years in the future, is a natural phase in the life cycle of galaxies. It reminds us that the universe is a dynamic and evolving arena, governed by the relentless pull of gravity and the intricate dance of matter and energy. This ongoing story, spanning from the quiet swirl of gas clouds in stellar nurseries to the violent coalescence of black holes, underscores the importance of continued observation and theory. The advancements in telescopes, ranging from ground-based observatories to space telescopes like the James Webb Space Telescope, are enabling astronomers to peer into the distant universe, witnessing galaxies in various stages of merging. Such observations provide vital snapshots across cosmic time, helping us understand not just what will happen when our galaxy meets Andromeda, but also how similar processes have shaped the universe we see today. In all its facets, the galaxy collision exemplifies the fundamental principle that change is the only constant in the cosmos. Over unimaginably long periods, these interactions forge the structures and diversity we observe in the universe. They influence everything from star formation to galaxy morphology, from black hole growth to the distribution of cosmic matter. Studying these grand cosmic events equips us with a deeper appreciation of the universe's complexity and the forces that drive its continual transformation. As our scientific knowledge continues to expand, future discoveries will undoubtedly refine our understanding of galaxy mergers. We may uncover new physics governing black hole behavior, the role of dark matter in galaxy interactions, or the detailed dynamics of gas flows during collisions. Each breakthrough will deepen our comprehension of the intricate balance of forces that has sculpted the universe over billions of years, guiding us toward a more complete picture of our cosmic origins and destiny. Meanwhile, on a human timescale, the knowledge that such processes are unfolding across incomprehensible distances and epochs serves as a humbling reminder of our place in the universe. It connects us to a history far beyond human experience and inspires a sense of wonder about the grand cosmic story in which we are both spectators and participants. The eventual collision of the Milky Way and Andromeda is a chapter in that story, one written in the language of gravity, matter, and time, and unlocked through the persistent efforts of science to understand the universe's deepest secrets. As the two galaxies draw closer together, the gravitational forces between the Milky Way and Andromeda become increasingly intense, setting the stage for a series of complex and spectacular interactions. This gravitational tug-of-war is not simply a matter of two objects colliding head-on. Rather, it involves an intricate ballet of stars, gas, and dark matter, all responding to the mutual attraction that slowly accelerates them toward one another. Interestingly, because galaxies are mostly empty space, the chance of direct star-to-star collisions during such mergers remains exceedingly small. Stars are separated by vast distances, measured in light years, so most will pass by one another without incident. Instead, what primarily occurs are gravitational disruptions that dramatically reshape the structure and composition of each galaxy. As the galaxies begin to intertwine, they're halos of dark matter, an elusive substance that makes up roughly 85% of the universe's matter, play a crucial role in guiding the merger process. Dark matter forms a vast, invisible scaffold extending well beyond the visible parts of galaxies. During the collision, these halos also interact and merge, providing the gravitational framework that influences the paths of stars, gas clouds, and the galaxy's overall angular momentum. This dark matter component acts much like a gravitational glue, ensuring that even as the luminous structures collide and distort, the overall system remains bound together. Over time, the dark matter halos of the Milky Way and Andromeda will overlap and merge, helping to stabilize the outcome of the collision and influencing the final shape and size of the new galaxy. As the two galaxies continue their cosmic dance, their mutual gravity strips stars, gas, and dust from each galaxy, creating long, luminous streams known as tidal tails. These are especially striking features, vast arcs of material extending hundreds of thousands of light years into space. Tidal tails are formed because differential gravitational forces stretch and pull material out of the galaxy's disks, flinging stars and gas into elongated shapes. Observations of distant merging galaxies often reveal these spectacular structures as bridges and plumes connecting the colliding systems. Tidal tails serve as evidence of the violent dynamics at play and can last for hundreds of millions to billions of years, gradually dispersing into the surrounding intergalactic medium or falling back into the merging galaxies. In addition to the gravitational warping of structural components, the collision triggers intense periods of star formation. When gas clouds are compressed and shock-heated during interactions, they can cool and condense more efficiently, collapsing under gravity to form new stars. These starburst events can produce dozens or even hundreds of times more stars than usual over relatively short cosmic timescales. As a result, the merging process becomes a cosmic factory, dramatically altering the recipient galaxy's stellar population and overall brightness. The formation of new stars in tidal tails or in the central regions can be quite prolific, leading to the emergence of bright, blue star-forming regions, sometimes referred to as starburst knots. These regions can serve as laboratories for understanding how interactions influence star formation and galaxy evolution. The increase in star formation activity during a merger also impacts the galaxy's gas content and future evolution. As gas is funneled toward the center of the combined system, it can feed the active nuclei of supermassive black holes lurking in the galactic cores. These central engines can become temporarily hyperactive, transforming into active galactic nuclei and releasing tremendous amounts of energy across the electromagnetic spectrum. This activity can eject gas and dust from the central regions, effectively quenching subsequent star formation in those zones, a process known as feedback. Such feedback mechanisms are crucial in regulating the growth of the galaxy's central black holes and their stellar populations, shaping the final properties of the merger remnant. Over the course of millions to billions of years, the colliding galaxies gradually lose their distinct identities, merging into a single, more massive galaxy. This remnant typically exhibits a morphology quite different from the original spiral or disc-like structures of its progenitors. Instead, the final galaxy often takes on the form of an elliptical galaxy, a rounded, more featureless system with a smooth distribution of stars. This transformation results from the violent mixing of stellar orbits during the merger, which erases the original spiral arms and bars. The stars in the new elliptical galaxy tend to have more random, isotropic orbits, giving the galaxy its characteristic rounded shape. Interestingly, this process of transformation can leave behind subtle clues that scientists use to trace back the galaxy's history. For example, stellar streams, trails of stars pulled from disrupted smaller galaxies or from the outskirts of the merging galaxies, act as cosmic fingerprints of past interactions. By studying the distribution and composition of these streams, astronomers can reconstruct the merger history and understand the underlying dynamics at play. Similarly, shell-like structures observed around some elliptical galaxies are thought to be remnants of previous accretion events. These features serve as cosmic archaeological records, revealing the galaxy's evolutionary past and the ongoing process of cosmic assembly. Black holes at the centers of galaxies also undergo significant changes during mergers. As the supermassive black holes in each galaxy are drawn toward the center of the combined system, they eventually form a binary black hole pair that continues to spiral inward over cosmic timescales. The eventual coalescence of these supermassive black holes releases gravitational waves, ripples in spacetime, that propagate outward at the speed of light. While detecting these waves from such distant and massive events remains a formidable challenge, future observations with advanced gravitational wave observatories promise to shed light on these extraordinary phenomena. The merging black holes can also influence the core properties of the galaxy, creating a cleared-out or core-scoured region, an observable feature in many elliptical galaxies today. The total energy released during the final black hole merger can be immense, sometimes amounting to a few percent of the combined black hole's mass energy, as described by Einstein's famous equation, E equals mc2. These energetic emissions can further disturb the surrounding gas, either suppressing or triggering new episodes of star formation. The feedback from black hole activity during mergers serves as a vital component in models of galaxy evolution, helping to explain why many massive galaxies end up as quiescent, elliptical systems with little ongoing star formation despite abundant gas supply potential. While the physical processes involved in galaxy mergers are tremendously complex, astrophysicists utilize sophisticated computer simulations to understand and predict their outcomes. These simulations incorporate gravity, gas dynamics, star formation, feedback from black holes, and the influence of dark matter to recreate galaxy interactions in detailed virtual experiments. By comparing these models with astronomical observations, scientists refine their understanding of how galaxies grow and change over cosmic time. Such simulations have shown that the eventual product of a major collision between large spiral galaxies, like the Milky Way and Andromeda, is often a massive elliptical galaxy, characterized by a mixed stellar population, little to no gas, and a dominant central black hole. Looking beyond the immediate effects, galaxy mergers also influence the broader environment. The streams and shells of stars and gas ejected during collisions enrich the intergalactic medium, dispersing metals, elements heavier than helium, across vast regions of space. This process contributes to the chemical evolution of the universe, influencing future generations of star and galaxy formation. Moreover, large-scale filamentary structures of dark matter and gas, identified through large surveys, serve as highways guiding galaxies toward their ultimate interactions. Understanding how mergers unfold within this cosmic web helps astronomers place the Milky Way-Andromeda collision within the grander picture of large-scale cosmic structure formation. Eventually, when the Milky Way and Andromeda do collide, the event will unfold over hundreds of millions of years. During this period, the night sky from Earth's perspective will undergo profound changes. The familiar spiral arms of the Milky Way will become distorted, and in some regions, the stars will appear to be dragged into new configurations. The Andromeda galaxy will gradually encroach upon our own, creating a cascading series of gravitational interactions. Still, remarkable as it sounds, these changes will happen slowly, far slower than human lifetimes, affording future generations the opportunity to observe, measure, and interpret the ongoing transformation. It's important to remember that, despite the dramatic and violent nature of galaxy mergers, these are fundamentally natural processes governed by gravity, the same force that keeps our planet in orbit around the sun. Over the course of billions of years, the universe continually reshapes itself, building larger structures from smaller ones, transforming galaxies through interaction, and recycling matter and energy in a cosmic cycle. Our Earth, our Sun, and our galaxy are all part of this vast, ongoing evolution, which demonstrates the dynamic, ever-changing character of the universe. In truth, contemplating the future collision of the Milky Way and Andromeda reveals both our cosmic ignorance and our capacity for scientific discovery. While many details remain to be understood, such as the precise timing of the merger, the role of dark matter, and the potential for life to survive in such an event, the fundamental principles guiding these processes are well established. The collision is a testament to the power of gravity and the interconnected nature of cosmic structures. It also underscores the importance of continued observation, experimentation, and theoretical modeling to deepen our understanding of the universe's grand design. As we look ahead, advancements in technology will enable astronomers to peer even more deeply into the universe, capturing the merging process at various stages across different galaxies. With the next generation of telescopes, such as the Vera C. Rubin Observatory and the European Extremely Large Telescope, we anticipate a flood of new data, images, spectra, and gravitational waves that will refine our models and perhaps reveal surprises along the way. Each discovery will bring us closer to comprehending the full life cycle of galaxies, how they form, grow, interact, and eventually evolve into the majestic structures that adorn the night sky. Through this understanding, we come to see that galaxy mergers are not merely destructive events, but critical ingredients in the ongoing story of cosmic evolution. They generate diverse structures, initiate new generations of stars, and shape the universe's large-scale architecture. In the end, our own galaxy's future encompasses these universal principles, emphasizing that even the most seemingly stable cosmic entities are engaged in an unending process of transformation, an eternal dance choreographed by the fundamental laws of nature. As the Milky Way and Andromeda continue their slow approach over the coming billions of years, astronomers anticipate that their combined gravitational forces will lead to a spectacular and complex dance, culminating in a cosmic merger. This process is far from sudden. Instead, it unfolds gradually, with multiple rounds of gravitational interactions that ripple through both galaxies. During these encounters, the galaxies will distort, stretch, and pull at each other's stars and gas, creating stunning tidal tails, long, flowing streams of stars and gas that extend outward like celestial ribbons. These features are common in observed galaxy collisions and serve as visual evidence of the immense gravitational forces at play. They also reveal how galaxies exchange material during interactions, with some gas and stars being ejected into intergalactic space, while others are funneled toward the galactic centers, fueling black hole activity or triggering new star formation. One critical aspect of this merging process involves the intermingling of the galaxy's gas clouds. When two galaxies collide, their vast reservoirs of gas can compress dramatically due to shock waves generated during the interaction. This compression can ignite intense bursts of star formation, often called starbursts, where millions of new stars are born within a relatively short cosmic timescale. These starbursts can dramatically alter the appearance of the merging system, producing luminous regions of young, hot stars that glow brightly across ultraviolet and infrared wavelengths. However, as the merger progresses, a significant portion of this cold gas can be consumed or heated, reducing the availability of raw material for future star formation. This transition from active starbirth to a more quiescent state is a common feature observed in many evolved galaxies, suggesting that galaxy mergers play a pivotal role in transforming vibrant, star-forming spirals into calmer elliptical galaxies. The gravitational tug-of-war during a merger also causes the motions of stars within each galaxy to become increasingly chaotic. Instead of orderly orbits within a disk, stars will follow elongated, randomized paths as their original structures are disrupted. Over time, the combined gravitational influences cause the stellar populations to settle into a more spheroidal configuration. This process explains why the remnant galaxy often exhibits an elliptical shape, smooth, rounded, and lacking the distinct spiral arms familiar in galaxies like the Milky Way. Such elliptical galaxies tend to host mostly older stars, with less ongoing star formation, reflecting their turbulent past. Interestingly, the remnants of galaxy mergers tend to be more massive and contain more stars than their progenitors, contributing to the universe's overall mass assembly and the growth of the characteristic giant ellipticals observed in galaxy clusters. Black holes nestled at the centers of galaxies also undergo profound changes during these cosmic mergers. As the galaxies draw closer, their central supermassive black holes are drawn toward one another, eventually forming a pair that orbits at the core of the newly merging system. When these black holes get close enough, they begin to spiral inward as gravitational waves are emitted, ripples in spacetime that carry away energy, allowing the black holes to coalesce into an even more massive black hole. This process can release enormous amounts of energy, sometimes equivalent to a few percent of the combined black hole mass, illuminating the universe with powerful electromagnetic signals known as gravitational wave events. Although detecting such waves from distant galaxy mergers is challenging with current technology, future advancements, such as space-based gravitational wave observatories, may enable astronomers to observe these spectacular black hole mergers directly. The activity associated with these black holes, called active galactic nuclei, AGN, can profoundly influence their host galaxies. As black holes accrete matter, they release energetic jets and radiation that can heat or expel gas from the galaxy's core, suppressing further star formation. This feedback mechanism is a key component in our understanding of galaxy evolution because it helps explain why many massive galaxies appear quenched. That is, they no longer actively form new stars despite possessing vast reserves of gas. Black hole feedback effectively regulates the growth of galaxies and their central black holes, establishing a delicate balance that shapes the life cycle of cosmic structures over billions of years. Scientists employ powerful computer simulations to explore these complex processes in exquisite detail. These virtual experiments incorporate the laws of gravity, the physics of gas dynamics, star formation recipes, black hole feedback, and the influence of dark matter, the mysterious, invisible substance that makes up most of the universe's mass. By adjusting the initial conditions, such as galaxy sizes, velocities, and compositions, researchers can predict how different merger scenarios unfold, compare these predictions with real astronomical observations, and refine their understanding of galaxy evolution. These simulations have consistently shown that major mergers, collisions between galaxies of comparable size, tend to produce the largest and most dramatic transformation, often resulting in giant elliptical galaxies. They also help elucidate the role of dark matter in guiding the large-scale structure formation, acting as a scaffolding that influences how galaxies move and interact within the cosmic web. Looking at the larger scale, galaxy mergers are interconnected with the universe's grand architecture. The cosmic web, an intricate network of filaments composed of dark matter, gas, and galaxies, serves as the universe's scaffolding, funneling galaxies toward one another through gravity's pull. As galaxies journey along these filaments, they can encounter nodes, regions where multiple filaments intersect, leading to a higher probability of interactions and mergers. Consequently, galaxy collisions are not isolated accidents, but part of a larger pattern of structure growth. These processes enrich the intergalactic medium with metals, heavy elements produced within stars and distributed during collisions, thereby influencing the chemical makeup of future generations of stars and galaxies. The expelled gas and metals mix into the surrounding space, enriching it and fostering the conditions for new star formation in different regions of the universe. This ongoing cycle exemplifies how galaxy mergers contribute to the universe's chemical enrichment and structural evolution on an immense scale. As the cosmic clock continues to tick forward, the eventual collision of the Milky Way and Andromeda will unfold over hundreds of millions of years, a timescale that on human scales seems almost incomprehensible, yet significant in cosmic terms. During this protracted period, multiple close encounters will occur, with the two galaxies gravitationally tugging on each other, distorting their structures, and triggering episodes of star formation. In the earliest stages, the night sky from Earth will remain familiar, although subtly altered. Distant stars will begin to shift, and the familiar spiral arms may start to warp or stretch. As the galaxies draw nearer, the night sky will become increasingly chaotic and spectacular. Our celestial neighborhood will be reshaped with new star streams and bridges of gas connecting the two galaxies. Eventually, the two galaxies will coalesce into a single, larger galaxy, likely an elliptical galaxy, over a time span spanning hundreds of millions of years. During this final merging phase, the stars themselves are unlikely to collide directly because of the vast distances separating individual stellar systems. However, the gravitational disturbances will send many stars on new trajectories, ultimately mixing the stellar populations and erasing the original spiral structure. The combined galaxy's core will host an even more massive black hole, a behemoth formed from the merger's black holes, which will likely continue to grow by swallowing surrounding gas and stars. Meanwhile, the gas reservoirs will have been largely depleted or rendered inhospitable for new star formation, leading the final galaxy to resemble a quiescent elliptical, an old, luminous, and relatively inactive stellar system. It's also worth noting that, despite the colossal energies involved, many of the stars in the merging galaxies will survive the encounter relatively unscathed, continuing their journeys through the new galaxy. Our solar system, for instance, might be among the many stellar systems preserved in the aftermath, although its precise fate depends on the specifics of the encounters, such as whether it is pulled into the central regions or ejected into the outskirts. From our perspective, the night sky will be spectacularly transformed during these ancient cosmic events. The familiar spiral arms will dissolve into a smooth, spheroidal glow, and new clusters of bright, young stars will give way to the more subdued shimmer characteristic of elliptical galaxies. This transformation exemplifies how cosmic structures evolve through a combination of violent interactions and gradual relaxation processes. This immense, slow process highlights a fundamental principle of the universe. It is ever-changing. Even the seemingly stable, familiar galaxy we call home is part of an ongoing cycle, morphing over billions of years through collisions, accretions, and black hole activity. Our own galaxy's history includes countless minor mergers with smaller satellite galaxies, such as the Sagittarius dwarf galaxy, which have left minute but noticeable signatures in the Milky Way's stellar halo. The future merger with Andromeda is simply the next major step in this ongoing process of cosmic assembly. Understanding these events deepens our appreciation for the intricate, interconnected mechanisms shaping the universe. Galaxy mergers are not isolated disasters, but essential elements of cosmic evolution, creating the diversity of galaxy types we observe today, distributing the ingredients for future star formation across space, and influencing the growth of supermassive black holes that reside in the hearts of galaxies. The knowledge gained from studying these processes also sheds light on the origins of the structures we see in the universe, from grand, spherical elliptical galaxies to sprawling, complex spiral systems. Thanks to ongoing advancements in observational technology, scientists continue to improve their understanding of galaxy interactions. Telescopes capable of observing distant galaxies at various stages of merging provide snapshots of the process in action, revealing the detailed physics of tidal interactions, starbursts, and black hole activity. Gravitational wave detectors, enhanced by future space missions, promise to unveil direct evidence of black hole mergers in distant galaxies, offering new insights into the fundamental physics at play. On the theoretical side, simulations grow increasingly sophisticated, incorporating the influence of dark matter, magnetic fields, and feedback processes with ever greater accuracy. Looking ahead, these technological and scientific advances will allow us to model the Milky Way's future with increasing precision. We may someday predict exactly when the plunge will begin, how the star's orbits will be affected, and what the ultimate structure of the remnant galaxy will look like. Such knowledge will deepen our understanding of the life cycles of galaxies and the universe as a whole, providing context for the formation and evolution of everything we see in the cosmos. While the collisions and transformations may seem distant and abstract, they fundamentally demonstrate the universe's relentless capacity for change, where nothing remains static, and even the most enduring structures are subject to the laws of gravity and cosmic evolution. As we continue our exploration, our curiosity pushes us to decode these grand processes, further revealing how the universe assembles itself, star by star, galaxy by galaxy. These events are not only cosmic spectacles, but also vital chapters in the ongoing story of the universe's growth and transformation. A story that stretches back billions of years and will continue far into the future, shaping the universe's destiny in ways we are only beginning to comprehend.